April 12, 1937. A narrow brick workshop stands at the edge of the British Thomson Houston Works in Rugby, Warwickshire. Morning light cuts through the factory's corrugated windows, falling across a cluttered wooden bench. Sheets of aluminum, oil-stained gloves, and brass tubing lie scattered beside a hand-cranked lathe. The air carries a faint metallic odor, burnt lubricant and cold steel. Against the far wall, a compact engine rests on a trestle stand, its casing pitted from repeated reassembly. No military insignia marks it. A handwritten tag, looped through wire, reads simply, Whittle Unit. Two men in overalls adjust the compressor casing. Their tools are standard workshop issue, not military. One of them, lean and soft-spoken, keeps a small notebook open beside the test rig. His name is Frank Whittle, age 29, a Royal Air Force officer working on unpaid leave. The RAF does not fund this project. The British Air Ministry, in a formal letter 6 months earlier, had described his proposal as impractical. The engine in front of him represents the persistence of private capital and borrowed time. The compressor assembly hums faintly as the starter motor turns. A shrill whine builds, rising, falling, then stalling with a dry metallic cough. Smoke drifts toward the open door. The men step back, expressionless. Whittle notes the readings, combustion incomplete. Compressor surge at 4,000 RPM. He closes the notebook and resets the starter switch. Outside, an engineer from British Thomson Houston listens through the doorway. His clipboard bears the ministry's inspection seal. He records the observation without comment. To him, the contraption is curious but peripheral, a small experimental turbine unlikely to replace the piston engines filling the hangars at RAF Cranwell. Across Britain that spring, aircraft factories continue producing radial and inline piston engines by the thousands. Rolls-Royce, Napier, and Bristol dominate the market. Each new design chases incremental gains, 20 more horsepower, 10 fewer kilograms. No one, except Whittle's small team, is working on propulsion without pistons. The test continues. The starter whines again, and this time the engine ignites with a hollow thump. A flame jet bursts from the exhaust cone, steady and pale blue. The workshop shudders under the vibration. Instruments rattle on the bench. Pressure gauges quiver upward, 6,000 RPM, then 7,000. The noise grows to a high-pitched roar, unlike any known aircraft engine. For 30 seconds, the machine sustains power before the fuel feed chokes and dies. Silence returns, leaving the smell of burnt kerosene. Whittle switches off the ignition and inspects the fuel manifold. His assistant, Joseph's Jim Colling, records temperature and pressure readings. Both work in near silence, interrupted only by the ticking of cooling metal. A nearby calendar still shows March, the days unmarked, a forgotten detail in a room consumed by repetition. In a ledger recovered from the site decades later, the entry for that morning reads: Sustained combustion. Short duration. Power trend positive. Proceed with redesign of diffuser section. At the time, the result draws little notice. The Ministry's Air Committee reviews the report and files it under private research, limited scope. Yet within those lines, the faint, pencil-scrawled words of a working engineer, lies the first functioning British turbojet. Whittle's tools are ordinary, hand drills, soldering irons, sheet metal shears. The engine's casings are hand-fitted. Each section must be heated and hammered to seat properly. The team uses surplus ball bearings and recycled piping from the factory's electrical turbine stock. Their funding comes from a private backer, Major Maurice Bonham Carter, who mortgaged part of his estate to sustain the work. Every few weeks, officials from the Air Ministry's technical department visit to monitor expenditure. They stand at the edge of the workshop, observing without participation. When Whittle mentions the compressor's high efficiency, they remind him of the department's earlier evaluation, unsuitable for military adoption. By evening, the small shop falls quiet. The lathe is wiped down, the test unit covered with canvas. Outside, the industrial district hums with the sound of lorries leaving the main gate. In the half-light, Whittle locks the door and pockets the key. His notebook remains under the engine stand, a few pages filled that day with pressure ratios, exhaust temperatures, and one brief remark, "Progress steady." No headlines record the event. No officials are informed. Yet the moment marks the first controlled demonstration of a self-sustaining gas turbine for flight, a machine small enough to fit beneath an aircraft wing, powerful enough to eliminate the propeller itself. According to Science Museum archives, the original Whittle unit achieved continuous operation later that month. It reached speeds exceeding 13,000 revolutions per minute, an order of magnitude above conventional aircraft engines. The test site, a nondescript shed at Rugby, would later be recognized as the birthplace of jet propulsion in Britain. The film reel from that day no longer exists. Only Whittle's notes remain, precise, economical, and calm. Each line describes not invention, but verification. By June 1937, the workshop in Rugby had become a pattern of repetition. Each morning began with the same ritual: fuel lines checked, ignition circuits tested, notebook placed beside the compressor rig. The air inside the shed grew heavy with kerosene vapor. On the concrete floor, dark stains marked every failed run. Between them, a thin trail of burn marks traced where exhaust flames had once struck the wall. Frank Whittle's days were divided between RAF duty reports and experimental work for Power Jets Limited, the private company he had founded 2 years earlier with 2 friends from Cranwell. Officially, he was on detached service. In practice, he was running Britain's first independent jet propulsion company. The Air Ministry remained skeptical. Its correspondence, preserved at the National Archives, shows bureaucratic caution, practicability unproven. Thermal stress and material fatigue likely prohibitive. Inside the shed, the experiment continued regardless. The compressor casing, rebuilt for the 3rd time, was now reinforced with machined steel bands. The turbine blades, hand-filed by Colling using discarded turbine steel, shimmered under the bench light. When assembled, the engine weighed barely 200 kilograms. Whittle's technical aim was simple but radical: continuous combustion. Piston engines produced bursts of power through timed explosions. His turbine sought to generate uninterrupted thrust by feeding air and fuel through a rotating compressor. To achieve this, he designed a diffuser to slow the air and raise pressure before ignition, a task that, at the time, had no industrial precedent. On June 22, the team prepared for the 39th test. The walls had been lined with asbestos panels borrowed from a power station. A new fuel injector had been installed, made from a modified oil nozzle used in household boilers. The starting motor was wound from surplus generator parts. Nothing in the room looked like the beginning of aviation's next era. At 10:14 a.m., the starter engaged. The engine whined, coughed once, then ignited with a clean roar. The vibration traveled through the concrete floor. Pressure gauges climbed past 12,000 revolutions. A narrow blue exhaust burned steady, uninterrupted for 51 seconds, the longest duration yet. Colling recorded the readings. Whittle adjusted the throttle by millimeters, watching exhaust pressure rise evenly across the manifold. No explosion, no stall. Only a continuous jet. He nodded once and cut the fuel supply. The engine spooled down with a sound like wind through a tunnel. The notebook entry that morning read: stable combustion. No detonation. Sustained operation indicates viability of principle. Across the corridor, British Thomson Houston supervisor observed from behind the safety screen. The company's management had grown uneasy with the experiment. Their electrical engineers had little interest in aviation, and the insurance division had voiced concern about uncontrolled flame discharge. A week later, the firm requested that Whittle relocate the test to a more suitable site. It was an inconvenience that changed aviation history. By late summer, the project moved to a disused foundry in Lutterworth, Leicestershire. The space was larger, the ceiling higher, the walls reinforced with brick. Here, Whittle's team assembled what they called the W.1 engine, a complete flight-ready prototype. It featured a centrifugal compressor, annular combustion chamber, and single-stage turbine. To the untrained eye, it resembled a polished steel drum. To engineers, it represented the first practical turbojet. When the first W.1 tests began in April 1938, observers from the Air Ministry were invited. Two arrived, Squadron Leader Griffith and Engineer Inspector Scott. They carried notebooks but offered no assistance. According to the test log, Griffith asked a single question during setup: "What is your estimated thrust?" Whittle answered without hesitation, £1,000. The test ran for 2 minutes before the turbine bearings seized. Post-test analysis revealed overheating in the rear casing. Whittle marked the cause as lubrication failure, rectifiable. His calm precision contrasted sharply with the enormity of what had just occurred. A jet engine had run continuously under its own power, generating measurable thrust. Outside, in the courtyard, exhaust soot coated the walls in a straight, symmetrical line. The mark remained visible for years, even after the foundry resumed normal work. According to the Science Museum's preserved records, the W.1 achieved its first successful full-power run on April 12, 1938, exactly 1 year after the Rugby prototype. Thrust measured 860 pounds. Rotational speed 17,000 revolutions per minute. No newspaper reported the result. The Air Ministry filed it under experimental. Yet among Whittle's 3 engineers, the sound of that steady, unbroken roar signified something irreversible. A machine had breathed without pistons. By early 1939, the Lutterworth foundry had taken on the rhythm of an organized laboratory. The roar of turbines had replaced the hammering of the old casting floor. Every surface carried a film of soot and graphite. The smell of oil and burnt metal lingered even after ventilation fans ran for hours. Power Jets Limited now employed 12 men, all working in secrecy. Each component arriving by lorry was labeled under coded purchase orders to avoid attention. The Air Ministry had agreed to partial funding that year, though with strict oversight. What began as a dismissed idea had become a classified project under military supervision. The data sheets from that period record the evolution of a single principle into a system. Thrust efficiency improved by 9% after the adoption of a new diffuser design. Fuel consumption dropped proportionally. Compressor pressure ratios rose from 2.5 to 3.6 to 1, and turbine temperature margins exceeded 600 degrees Celsius. The results, typed in carbon copies and stored in plain envelopes, represented the first measurable evidence that jet propulsion could power a combat aircraft. When Whittle presented his findings to the Aeronautical Research Committee that February, the reaction was polite but restrained. The older engineers, trained in the piston era, questioned the material endurance of turbine blades at such temperatures. Whittle's reply was factual, not persuasive. Nickel-chrome alloys retain integrity at tested loads. His tone resembled an engineering briefing, not a sales pitch. His years of skepticism had trained him to argue only through data. The breakthrough came quietly. Rolls-Royce engineers, after reviewing Whittle's performance charts, calculated that his prototype's thrust-to-weight ratio matched that of existing fighter engines. The difference was in potential: no propeller losses, no reciprocating parts, minimal vibration. An internal memo from the firm dated May 1939 described it as operationally revolutionary if scaled for flight. Construction of the first flight unit began that summer. Designated the Whittle Supercharger Type W.1X, it was assembled in a small hangar at RAF Cranwell, not far from where Whittle had once been a cadet. The airframe chosen for testing was an experimental twin-seat aircraft built by the Gloucester Aircraft Company. Officially, it was a technology demonstrator. In reality, it was Britain's first jet-powered aircraft. The data logs from those weeks reveal a gradual refinement. Each startup lasted longer, each bearing survived higher temperatures, each turbine cycle produced steadier exhaust flow. Engineers measured vibration patterns with handheld probes and recorded them in millivolts. Fuel injectors were recalibrated with micrometer precision. By August, the W.1X could sustain full throttle for 4 minutes without component failure. Observers from the Air Ministry arrived unannounced during one of the tests. They watched as the compact silver cylinder screamed to life, its sound filling the hangar with a tone unfamiliar to all present. The noise was continuous, unwavering, mechanical in its purity. When the fuel line was cut, the engine slowed gradually, not through misfire or detonation, but through the gentle decay of momentum. The visiting officers exchanged few words. The report they filed later used only one phrase to describe the event: performance confirmed. For Whittle, the realization arrived not in triumph but in recognition. The numbers before him proved the point he had argued for nearly a decade. The jet engine was no longer an idea, it was a tested mechanism capable of sustained flight thrust. His earlier sketches, the pencil drawings from 1929 that the ministry had once annotated as theoretical, now matched the readings from calibrated instruments. In his evening notes, he avoided reflection. Each page listed data only: shaft speeds, air mass flow, pressure recovery coefficients. Yet between those lines existed a quiet acknowledgement that the future of flight had shifted. What had begun in a brick shed with recycled bearings and hand tools now generated enough power to propel an aircraft beyond the limits of piston design. At the Science Museum decades later, the W.1 unit would be displayed behind glass. Visitors would see a compact cylinder of steel and brass, unremarkable at first glance. Few would realize that in 1939, the machine had already achieved a thrust of 1,240 pounds, verified by independent measurement, making it the most efficient power unit of its kind in the world. According to post-war evaluations from the Royal Aircraft Establishment, Whittle's W.1 achieved a specific fuel consumption 1/3 lower than any comparable engine tested before 1940. These figures, once confidential, later appeared in the technical annals of jet propulsion, confirming what Whittle had demonstrated in silence. The realization was neither celebrated nor dramatic. It arrived as a set of readings, stable and repeatable. A small British workshop had proven that controlled combustion, continuous and compact, could lift an aircraft through pure jet thrust. The data spoke for itself, calm and absolute. By the spring of 1941, the quiet persistence that had begun in Rugby reached its first public threshold. The Gloucester E.28U-39, fitted with Whittle's W.1 engine, stood at the edge of the runway at RAF Cranwell. Its airframe bore no markings of distinction, an unpainted test aircraft with smooth aluminum skin and narrow intakes flanking the nose. The day was cold and bright, the kind of clear Lincolnshire morning ideal for trials. Few observers were present. The ministry had not announced the test, only senior officials, ground crews, and Whittle's engineers attended. At 6:45 a.m., the jet engine ignited. The roar that followed was unlike any propeller start. It built as a single note, rising without interruption until the aircraft itself seemed to hum. Flight Lieutenant Jerry Sayer, the pilot, advanced the throttle gradually. The E.28-39 began rolling down the runway, its acceleration smooth and linear. Without propeller torque or vibration, the machine gained speed in near silence, wheels lifting cleanly from the tarmac. For 17 minutes, it flew at an altitude of 1,000 feet, circling above the airfield at over 300 miles per hour. Whittle stood near the hangar doors, his hands in his coat pockets, eyes fixed on the aircraft until it returned to land. The touchdown was steady. Sayer taxied to a stop, cut the fuel, and removed his helmet. His comment to Whittle was brief: "She flies beautifully." The engine had functioned flawlessly. In the official log, the test director recorded, "Flight complete. No mechanical fault. Thrust stable throughout." From that morning onward, British aviation entered a new register. The Air Ministry, which had once dismissed Whittle's design as speculative, authorized immediate development of production models. The experimental company, Power Jets Limited, was placed under partial government control and granted priority access to materials. Within weeks, the first plans were drawn for a twin-engine combat aircraft, later known as the Gloucester Meteor. The technical data from the Cranwell flight confirmed performance predictions almost precisely. The W.1 delivered 860 pounds of thrust, producing a sustained climb rate surpassing contemporary piston fighters. Temperature and pressure readings showed consistent balance between combustion and turbine output. For the first time, engineers could measure thrust as a steady physical quantity, not the byproduct of explosion and mechanical translation. In that data, the implications were clear. A jet-powered aircraft could maintain speed independent of air density, allowing higher altitude and greater endurance. Propellers, bound by their aerodynamic limits, could no longer define performance. The margin between existing fighters and the next generation had already been crossed. Whittle's own reflections, recorded years later, remained restrained. He noted only that the problem was never flight, it was faith. His tone in interviews matched the voice of his notebooks: technical, calm, understated. He had seen his idea move from a garage experiment to a functioning aircraft within less than a decade, yet his language never changed. Every breakthrough appeared as an entry, a measurement, or a percentage. Post-war assessments by the Royal Aircraft Establishment traced the immediate effects of his work. Between 1942 and 1945, jet propulsion expanded from a single British prototype to a global competition. Germany fielded the Messerschmitt Me 262, the United States developed the Bell P-59 and later adopted British engine blueprints. Each design, regardless of national origin, owed its core configuration, centrifugal compressor, annular combustion chamber, single axial turbine, to Whittle's proven model. In the decades that followed, the concept scaled exponentially. The same thermal cycle that once filled a small brick shed now powered intercontinental flight. Commercial airliners, military bombers, and experimental rockets all traced their lineage to the quiet line of data recorded in Lutterworth in 1939. The transition from reciprocating to continuous power changed not only aircraft design but the geography of the modern world. Inside the Science Museum in London, the original W.1 rests behind tempered glass. The casing shows burn marks where fuel once scorched its surface. Small placards explain its components: compressor, diffuser, turbine, exhaust cone. Visitors stand a moment, then move on, unaware that the polished artifact before them was once considered a personal obsession unworthy of funding. On the display plaque, one inscription quotes Whittle himself: "A nation that fails to back its innovators loses more than invention, it loses initiative." The words appear modest but precise, a reflection of the man who wrote them. The quiet engine that began as a private hobby in a rented shed had become the blueprint for the modern jet age. Its success was not born from institutional support or wartime urgency, but from method, repetition, and faith in measured truth. Every revolution it inspired, every aircraft that rose beyond the sound of pistons, began with that same steady sound recorded in his notes, a sustained, even roar that did not end until the fuel ran out. According to post-war debriefs preserved at the Science Museum archives, the total cost of Whittle's first working engine amounted to less than £6,000. In engineering terms, it was one of the most cost-efficient breakthroughs in history. The world that emerged from it, fast, connected, and airborne, was built not from the noise of ambition, but from the quiet certainty of a machine that worked exactly as designed. By 1943, Britain's secret work on jet propulsion had shifted from experiment to deployment. The Power Jets facility at Lutterworth expanded under government control, its brick walls reinforced and its staff multiplied tenfold. Whittle, now an RAF officer on special assignment, directed operations from a modest office filled with blueprints, flight data, and fuel sample jars. The tone of his reports remained clinical, pages of typed observations on thrust curves, alloy fatigue, and compressor efficiency. The war outside the laboratory barely entered his vocabulary. The Gloucester Meteor, designed around his W.2B engine, progressed toward flight testing. In hangars across the Midlands, teams assembled nacelles of polished steel, aligning turbine housings with micrometer precision. Each engine carried hundreds of hand-inscribed part numbers, most produced by craftsmen who had never seen an aircraft in flight. Rolls-Royce had joined production to assist with metallurgy and scaling. The turbine discs were now cast from heat-resistant mnemonic alloys developed under wartime secrecy. The first Meteor prototype ran its engines at full thrust in June 1943. Observers described the sound as a single unbroken tone, deeper than a propeller yet more constant than any piston roar. The vibration spread through the concrete apron and into the hangar structure. Whittle, standing near the instrumentation truck, measured pressure differentials and exhaust temperatures. His field notes from that day, still preserved in the Science Museum archives, include a simple assessment: thrust satisfactory. Stability within limits. Ready for flight trials. The war's urgency had transformed his invention from curiosity to necessity. German reconnaissance reports confirmed sightings of the Me-262, a jet-powered aircraft already in limited operation. The Air Ministry's directives shifted overnight. What had once been experimental propulsion was now priority weapon development. Power Jets was merged with larger state contractors. Whittle's direct control narrowed. He protested in memoranda but continued to provide technical oversight. The ministry's justification was strategic: Britain needed mass production, not private innovation. On July 2, 1944, the Meteor made its operational debut with No. 616 Squadron of the Royal Air Force. It intercepted a German VE-1 flying bomb over Kent and destroyed it by wing contact after cannon failure, a maneuver recorded in the squadron log as "Ram attack successful." The aircraft's top speed, measured at 410 miles per hour, exceeded every Allied piston fighter in service. The jet age had entered combat quietly, with no announcement beyond a line in the day's communiqué: enemy robot aircraft destroyed by jet-propelled fighter. Whittle was not present for that sortie. Illness brought on by exhaustion had forced him to a convalescence home near Cambridge. Years of constant work and administrative strain had weakened him. Yet even from rest, he continued to write letters to engineers in the field, correcting fuel metering ratios and urging precision in temperature recording. His influence remained technical, not managerial. By the end of 1944, more than 1,200 technicians were engaged in jet engine production across Britain. Each new unit was faster, lighter, and more efficient than the last. The Gloucester Meteor's subsequent models reached speeds above 500 miles per hour. These aircraft never fought in large-scale air battles, but they demonstrated conclusively that piston-driven aviation had reached its limit. The data collected from operational sorties confirmed the theory Whittle had pursued since 1929. Sustained propulsion through continuous combustion produced unmatched power-to-weight efficiency. The measured thrust-to-fuel ratio, recorded by RAF engineers, averaged 1.35 pounds per pound of fuel per second, figures once considered beyond physical reach. The turbines operated at 16,000 revolutions continuously for over an hour without bearing failure. Post-war analyses by the Ministry of Supply showed that a jet engine could deliver double the performance of a piston engine at half the mechanical complexity. The conclusion was written in the dry tone of official documentation: jet propulsion offers operational superiority at all altitudes exceeding 20,000 feet. Recommended as future standard. Within 2 years, the conclusion became doctrine. Rolls-Royce took over full-scale jet engine development. Power jets, absorbed into government research, ceased to exist as an independent entity. Whittle's patent rights were transferred to the Crown in exchange for compensation, £100,000, later adjusted for wartime inflation. In technical terms, his invention had moved beyond ownership. His final report to the Air Ministry in 1946 consisted of 12 pages. The last paragraph, written without emphasis, contained a single prediction: jet propulsion will enable sustained flight at speeds exceeding 600 miles per hour and altitudes above 40,000 feet. It would prove correct within 3 years. In the months that followed, Britain's first jet bombers, the de Havilland Vampire and the English Electric Canberra, took form from those predictions. Across the Atlantic, the United States invited Whittle to consult with General Electric and Bell Aircraft, where his early design notes guided the construction of America's first production jet. The same circular compressor geometry, the same blade curvature, the same proportional diffuser spacing, all replicated with American alloys and tooling. From a small garage experiment had grown an entire industry. The once rejected toy engine was now the basis for fleets, economies, and a new dimension of warfare. And through every variant, from the W.1 to the latest turbojet, one element remained constant: the sound that had filled the Lutterworth shed in 1937, a steady, continuous roar that signified progress measured not in noise, but in precision. In 1946, Britain's airfield stood quiet. Rows of jet prototypes lined hangars that only years earlier had been crowded with piston fighters returning from sorties. The war was over, but its engines still spun, testing new fuels and alloys in the subdued light of post-war reconstruction. Power jets had been nationalized under the Ministry of Supply, absorbed into the bureaucratic structure of state research. The name remained on letterheads, but the company no longer belonged to its founder. Frank Whittle, newly promoted to Air Commodore, worked within the system he had once challenged. His influence now filtered through committees, minutes, and classified memoranda. He arrived daily at the National Gas Turbine establishment in Farnborough, where a row of new test cells had been constructed in reinforced concrete. The sound within those bays was familiar, high-frequency whines rising into full-throated roar as engineers ran endurance trials on the W.2 and its successors. Data flickered across analog instruments. Pressure transducers recorded readings in ink traces, feeding into thick rolls of graph paper. Each run lasted precisely 10 minutes, followed by cooling and inspection. What had once been improvised in a brick shed was now an industrial routine carried out by hundreds of technicians. Yet Whittle's satisfaction was partial. He watched as larger firms, Rolls-Royce, de Havilland, Armstrong Siddeley, dominated jet development, refining his design for production airliners and bombers. His name appeared in the patent citations but seldom in executive reports. In a letter to his wife that year, he wrote plainly, "I see the engines everywhere now, but they seem no longer mine." The tone was factual, not bitter, as though he were cataloguing a natural consequence of invention. The world beyond Britain had moved swiftly to adopt his principle. American and Soviet engineers, drawing from wartime exchanges and captured data, developed their own turbines. The United States fielded the P-80 Shooting Star, the Soviet Union tested the MiG-9. Both owed technical lineage to the centrifugal compressor geometry Whittle had proven in 1939. Within 2 years, axial flow designs began surpassing his early models, trading simplicity for speed. The jet age was no longer theoretical. It had become global infrastructure. Back in Farnborough, the British Air Ministry began reclassifying jet research under civil aviation programs. A new directive, issued in 1947, called for commercial adaptation of gas turbine propulsion for transoceanic flight. Whittle, appointed as consultant, drafted early concept outlines for what would become the de Havilland Comet, the world's first jet airliner. His annotations emphasized fuel efficiency and maintenance accessibility, not prestige. Each margin note reflected the same precision he had applied in Lutterworth: line spacing, exhaust temperature, and turbine clearance written in pencil, never in prose. Public recognition arrived slowly. The press described him as the man who gave wings to the jet age, but in interviews he spoke with restraint. Asked whether he foresaw the global impact of his invention, he answered, "I foresaw efficiency." The rest followed from engineering. The words aligned with every report he had ever written: objective, unemotional, correct. By the early 1950s, the turbines derived from Whittle's first prototype-powered aircraft that crossed the Atlantic in half the time once required by propeller-driven transports. The RAF operated jet bombers that could fly higher than weather itself. The sound of the jet, once confined to a small workshop, now echoed above cities across the world. Flight had changed from mechanical endurance to continuous thrust, a transformation as quiet in its documentation as it was loud in its consequence. The data accumulated through those years told the story more clearly than any headline. Average operational thrust increased from 1,000 to 8,000 pounds within a decade. Material endurance rose by a factor of 5. Fuel consumption efficiency improved by 40%. These figures, drawn from reports by the Royal Aircraft Establishment, mapped the acceleration of an entire era. In engineering charts, progress appeared as a curve bending upward, steady and inevitable. In 1953, Whittle accepted a post as technical advisor to the Ministry of Supply but soon resigned for health reasons. The long years of work and stress had taken their toll. He relocated to the United States, where he lectured on propulsion engineering at universities and consulted for industry. When asked what moment had defined his career, he cited neither the first patent nor the first flight. Instead, he recalled the day at Rugby when the prototype first sustained combustion. "It wasn't victory," he said. "It was confirmation." The statement, calm and factual, encapsulated his entire method. He had not sought acclaim, only verification. The silence of that early test, broken only by a continuous, even roar, had carried the meaning that statistics and speeches could never capture. According to the Science Museum's post-war archives, by the time Whittle retired, over 40,000 aircraft engines in operation worldwide could trace their design lineage to his original centrifugal compressor patent. Each one, in its geometry and thermodynamic cycle, carried a fragment of the same discovery born in a British workshop under the dim light of 1937. No ceremony marked his departure from active research. His notebooks, filled with data tables and sketches, were transferred to the RAF College at Cranwell for preservation. Among the final entries was a short line written in pencil: "Combustion maintained. Principles enduring." The words read less as sentiment than as closure, a precise statement of fact that, even decades later, described both the machine and the man who built it. By the mid-1950s, the quiet idea that had once occupied a rented shed in Rugby had reshaped the world's sky. Airports expanded outward in rings of concrete, the sound of jet turbines became the new language of motion. Every major industrial nation adopted gas turbine propulsion as standard. What had begun as an individual's persistence now powered economies, connected continents, and redefined distance itself. In Britain, Rolls-Royce introduced the Avon and Conway engines, direct descendants of Whittle's centrifugal core, refined into axial flow precision. Each unit produced more than 10,000 pounds of thrust and could operate for hundreds of hours without overhaul. Engineers who had once visited Whittle's shed as skeptics now quoted his early equations in their design manuals. The language of piston ratios and crank bearings had been replaced by pressure gradients and turbine efficiency charts. The Air Ministry's records from 1956 describe an aviation network unrecognizable from the one Whittle entered as a cadet 25 years earlier. RAF squadrons flew at transonic speeds. Civil transports crossed oceans without refueling. Meteorology, navigation, and even geopolitics adjusted to new altitudes. The ministry's tone, as always, remained understated. Jet propulsion has matured into routine service. Whittle watched the transformation from abroad. At Ohio State University, where he taught gas dynamics, he lectured to students who had never known the world before the jet. His diagrams were exact, his voice calm, his sentences clipped. He referred to his invention not as revolution but as an engineering inevitability awaiting persistence. His colleagues noted that he rarely spoke of patents or recognition. His satisfaction remained technical, that the machinery behaved as the mathematics predicted. The United States awarded him the Daniel Guggenheim Medal for Aviation Achievement in 1957. During the ceremony, Whittle thanked not the committee but the technicians who had tightened bolts and adjusted flame holders when nothing seemed to work. His manner was reserved, almost military. Behind the applause, his eyes followed the projected image of the old rugby test stand displayed on the wall, the small, oil-stained bench where it had all begun. Meanwhile, commercial aviation accelerated beyond every wartime forecast. The de Havilland Comet entered service in 1952, followed by the Boeing 707 and the Douglas DC-8. Each bore engines derived from Whittle's thermodynamic cycle. The steady hum of turbines became the background of modern life, a constant mechanical tone stretching across hemispheres. The distances between cities compressed, nations remeasured time by flight schedules. Post-war economic studies from the British Ministry of Transport later credited jet propulsion with reducing intercontinental travel times by 60% within a single decade. Freight capacity increased fourfold. Tourism, trade, and global diplomacy reorganized themselves around jet timetables. A generation grew up for whom the sky was no longer distant. All of it traced, through industrial genealogy, back to the combustion principle tested in 1937, continuous thrust achieved through stable flow. In 1960, Whittle was knighted for services to aviation. The citation read simply, for the origination of the jet propulsion principle and its advancement to practical application. He accepted the honor quietly, standing in the same posture seen in wartime photographs, shoulders slightly forward, expression analytical. Later that evening, in an interview, he summarized his view of progress with characteristic detachment. It was never a sudden leap, only a series of verifications. At the Science Museum in London, curators began constructing a dedicated exhibit for the Whittle engine. Technicians cleaned the casing with soft brushes, tracing fingerprints preserved in the metal from the 1930s. Visitors leaned close to the information plaques, reading descriptions written in the same spare, factual tone that Whittle himself preferred. There were no heroic captions, no dramatization, only dates, pressures, and measured results. Across the Atlantic, NASA engineers cited Whittle's early compressor studies while developing rocket turbopumps for space vehicles. The continuity between jet propulsion and space propulsion was not philosophical but mechanical. The same calculations that had balanced airflow in Whittle's W.1 now governed liquid oxygen in rocket chambers. Each equation, pressure, velocity, temperature, followed his framework of controlled combustion. Whittle observed this with quiet satisfaction. In letters to fellow engineers, he described the space age as a natural extension of the gas turbine principle. When asked if he felt pride, his answer was consistent, only that the figures hold. His sense of accomplishment remained expressed in the language of verification, the bridge between hypothesis and measurement. By the late 1960s, the global jet fleet numbered in the tens of thousands. Military bombers exceeded the speed of sound. Passenger aircraft carried hundreds across oceans daily. The planet had contracted into a network of reachable points, its distances redrawn by turbines bearing the geometric signature of Whittle's 1930 sketches. At Cranwell, where he had once been a cadet dismissed as impractical, a bronze plaque was installed outside the main hangar. Its inscription was brief: "In this place began the jet age." Conceived by Air Commodore Sir Frank Whittle, proven by test, confirmed by flight. Beneath it, a single line added decades later summarized the scale of what followed: "From here, the world became smaller." The reflection within those words was not poetic but empirical. Jet propulsion had turned the mechanical into the global, the solitary experiment into infrastructure. And through every variant, from fighter engines to airliners to spacecraft, the lineage of form and function led back to the same scene in 1937 at a workshop, a young officer, and a sound that had never been heard before. By the late 1970s, Frank Whittle's name had settled into the technical lexicon of aviation, a figure invoked not as legend but as a constant, like thrust or lift. His work had become so deeply embedded in design and education that its origin seemed almost anonymous. Every engineering syllabus mentioned the Whittle cycle, every maintenance manual referenced centrifugal stage architecture, yet few who spoke the terms pictured the man behind them. That anonymity suited him. He had returned to Britain after years in the United States, his voice slower, his manner unchanged. Interviews recorded at the time show a calm tone, clipped and methodical, as though he were still dictating an engineering report. When asked about inspiration, he replied, "It wasn't imagination that mattered, it was patience." The statement carried the same balance he had maintained since 1937, restraint in expression, precision in thought. The world around him now ran on the principle he had verified in a rented shed. Transatlantic passenger flights crossed in under 7 hours. Jet cargo had replaced ships for urgent freight. Strategic bombers cruised higher than Everest. Satellites and rockets, drawing from gas turbine heritage, operated in thin air beyond the atmosphere. The steady roar of combustion had become the planet's background sound. At the Science Museum in London, the Whittle unit remained enclosed in glass, its surface dulled to a muted bronze. A new plaque listed its verified performance metrics: thrust, 1,240 pounds, RPM, 13,600, fuel type, kerosene blend number 3, operational date, April 1937. The accompanying description contained no adjectives, only outcomes. Visitors read and moved on, unaware that the small engine before them had once altered the future of every journey they would take. Archival assessments written after his death in 1996 reflected the same quiet tone. The Royal Aeronautical Society summarized his impact in measured terms: Whittle's work provided a continuous power source adaptable to all atmospheric speeds. His methodology established the foundation of modern propulsion engineering. No embellishment followed, no heroic phrasing. The record spoke through numbers and endurance. Historians later noted that his invention had emerged not from institutional ambition but from the persistence of one engineer working within rejection. He had no state laboratory, no research staff, no military funding at the start, only a principle that continuous combustion could outpace mechanical reciprocation. The fact that he proved it at all seemed, in retrospect, improbable. Yet every aircraft that lifted beyond propeller range testified that the improbable had become routine. In the years after his passing, flight continued to evolve along the trajectory he had opened. Turbofan engines refined the original concept into quieter, more efficient forms. High bypass ratios replaced brute thrust with measured airflow control. The core thermodynamics, compression, ignition, expansion, exhaust, remained unchanged. Even supersonic craft, and later hypersonic prototypes, still mirrored the diagrams he had drawn in pencil before the war. A 2007 engineering audit of the world's active jet engines found that 92% of all turbine designs used at least one structural or thermodynamic element first demonstrated by Whittle's Power Jets team. The remaining 8%, rocket-derived systems, were themselves direct descendants of turbine pump principles. His influence had become structural, no longer historical. In official commemorations, his image appeared modest, an officer in uniform, standing beside a small cylindrical engine on a metal frame. The composition never changed because it did not need to. That scene represented an exact equation, the human scale of persistence beside the mechanical scale of consequence. Near the end of his life, he wrote a short reflection for a lecture at the Royal Institution. It was never intended for publication but survives among his notes. The engine was not built to win a war or start a new one. It was built to make flight efficient. History took its own course afterward. The phrasing was restrained, the syntax mechanical, yet within it lay a full account of 20th century acceleration. His final recognition came not from ceremony but from continuity. The modern jet, in every form, from the smallest regional turbofan to the largest intercontinental airliner, carried the same cycle, the same geometry, the same logic of air and fire managed through precision. The principle proved once in a shed had become civilization's infrastructure. According to the Science Museum's closing annotation, the Whittle unit remains one of the few machines from the 1930s still able to function today with only minor restoration. Its bearings turn freely. The compressor spins in silence until air catches the blades and they hum, a faint mechanical tone, rising evenly. The curators describe the sound as almost human in its steadiness. But for Whittle, had he heard it again, it would have been merely data, a confirmation that pressure, fuel, and persistence remain in balance. History records no single moment of triumph, only a quiet sequence of verifications that turned an idea into an era. From that noise, the jet age began.